Hello and welcome back. In today's video, what we are going to learn is continuum and non-continuum fluids. We'll see why our fluid is divided into two groups, continuum and non-continuum, and what is its relation with studying the various fluid principles and various fluid properties. Let's start. I will start with continuum fluid first. So what is continuum fluid? Now for that, let us take example of fluid, whether it is at rest or it is in motion. We'll take example of fluid. Now let us suppose we want to define a property for this fluid, which is either at stationary or motion, doesn't matter. We want to define a property for this fluid. Let us say that property is density. Now when we define density of this fluid, we have two ways to define density. One is suppose average density, and we know density is the mass of unit volume. This is the density, and what we'll do is we will measure the entire fluid, and suppose its mass is m, and we will measure the volume it occupies. Suppose it occupies volume V, we'll divide mass by volume, and what we get is the average density of this fluid. Okay, we got the density. Now next question. This is a correct way of finding the average density of a fluid. Okay, but what we mostly need is, we occasionally need this average density. Mostly what we need is how density varies from point to point in a fluid. We are interested in knowing that. For example, a practical application. For example, we have atmosphere. Suppose this is the surface of the earth. Above it we have atmosphere, and as we go upwards, the density of the atmosphere decreases because the air becomes thinner and thinner. Density of the atmosphere decreases because the pressure decreases. Now what happens is, as we go up, density decreases, and we want to know how density varies from one point to another point in the vertical direction. We are not interested. Suppose for example, we know the average density. We cannot use that average density for air, that the average density of the entire air is this much, or the average density of this height up to this height of the air is this much. We are interested in knowing how density varies as we go up. So we want to know how density varies inside a fluid. This is the important question. So we have to come out of this average, and we have to find the actual density value at a point. Now let us find that. Suppose this is the point at which we want to find the density. What we'll do is we will zoom it in. Now when we zoom it in, we'll see this portion, something like this. Inside there will be fluid particles moving randomly. For example, one will be moving in this direction, another in this direction, another in this direction, another in this direction, another in this direction. In different random directions they will be moving, these fluid particles. And we know from kinetic theory of gases that the intermolecular spacing between liquids and gases is large as compared to the molecular diameter. If this small is the molecular diameter, the spacing between them is large in case of liquids and gases. Now keeping this point in mind, we wanted to know this point, density at this very point, and this point is at the center of this circle here. Density at this point. Now first problem, if we want to find density at this exact geometrical point in the fluid, first problem is that since these particles are continuously in random motion, at one moment particle will be at this point, fluid particle will be at this point, and at the next moment it will not be present at that point. So at one moment density gets defined, at another moment density does not get defined. So this is a big problem. We cannot define density at the exact geometrical point in the fluid because of this random motion of the particles and this intermolecular spacing. We may end up at the empty space, at the intermolecular spacing, and when that happens we cannot define density. Now this is the first problem that comes in our way in defining density at a particular point. Now, what is the workaround for this? What can we do in order to overcome this problem first? Now, then we can move on defining other properties, and then we can move on finding the changes in properties. Then we can relate those changes in properties with the system performance and all that. First, we have to know how to define these property changes, how property change from one point to another point. For that, we have to know what does defining a property at a particular point mean, and we did the exact analysis first, and we found that this is a problematic. There are intermolecular spacing point may end up at the empty space, and the density does not get defined and all that. Now, how to come out of this problem first? Now, one trick that we can use, using common sense, we can use one trick, and that trick is, instead of taking a exact geometrical point, we'll choose some volume around this point. We'll choose some volume. Suppose we have chosen this volume, still we can see, suppose there are, obviously the intermolecular spacing is not that large. Suppose there are these molecules. Now the trick for this problem, that the solution for this problem that we can think of first is, instead of taking the exact point, we'll take a small volume instead around that point at which we want to define density. So this is the volume that we took. Now when we take that volume, what will happen is we now have molecules inside that volume. If we take next equal volume, we will still be having some molecules inside it. Then we'll take another volume, we'll still having that some molecules inside this volume. And when we take this point, take a small volume around it, we will be having some molecules inside this. And this way, as we move from one volume to another volume, we will always move from point having molecules around to another point having molecules around. So this is one way of doing this. But here is the question for this solution for this trick that we used. One problem is how large this volume that should we choose, or how small should we choose this volume. We cannot keep it very large, we cannot keep it very small. Let us see why. First, why it cannot be very small. For example, if we choose, first of all, we want it to be as small as possible, because ideally it should be at a point. That's not possible. So let us choose a volume as small as possible, but we cannot choose extremely small. Why? Because if we choose the volume element in which there are, say, suppose 10 molecules, and due to random motion of these molecules inside this fluid, what will happen is some molecules comes out, some molecules go in. Maybe at an instant, out of 10, 3 come out. Out of 10, 3 come out. That is the 70% reduction of the mass, 70% reduction of the density. If at another instant 3 molecules go in, that is the 30% increment in the density. So that will be huge. So out of 10, 3 coming out, that will cause significant change in density, or gets added, that will cause significant increase in density. So the volume cannot be very small, containing tens or hundreds of molecules or thousands of molecules only. So this volume has to be large enough to contain as many molecules, as large molecules, so that if tens or hundreds come out, the overall change in mass will not be significant. So how small? It should be as small so that it contains still millions of molecules. Because if out of millions of molecules per second, suppose 10 or 100 or 1000 molecules go in or come out, that 1000 is very, very small, is negligible as compared to millions of molecules. So that way, that variation due to the randomness of the molecules will be neglected, will not be considered. So we know how small. It should be small enough to contain millions of molecules. That will take us out of the problem of randomness of the molecules coming out and going in. Number one. Number two, how large? We cannot keep it extremely small. We have to keep it large enough to contain millions of molecules. But how large we can go on the other limiting side? So how large? If we take it very large, so let's take it we can think of being on the safer side and take it large enough. So if we take it very large, if we take it like this much, what will happen is inside this volume that we have chosen, on one side we may have large number of molecules, on other side we may have smaller number of molecules. So inside this particular volume, density will be varying. So if we take it very large, what will happen is molecules in one region of this volume will be larger and molecules in another region will be smaller. So density will be varying within this volume, which we are trying to use to define density. So we have to, on the large end, we have to take that large in which the molecules are distributed uniformly, not large, very large, in which molecules on different regions may vary, and we may get varying density within that particular volume we are trying to define density within. So we have to find the optimal volume element, which on lower side contains millions of molecules, and on the other side the number of molecules will be distributed equally, and the density should be uniform in that volume. And what is that volume? First of all, that volume is called a representative elementary volume. Representative, we can call it representative elementary volume. That's the representative elementary volume. Let's call it delta V asterisk. Now, how much is this volume? This volume is 10 raised to the power minus 9 millimeter cube for all liquids, for all gases at 1 atmosphere pressure. For all liquids and for all gases at 1 atmosphere pressure, because for gases this spacing highly depends on, this intermolecular spacing highly depends on, or how many molecules will be in a particular volume, that highly depends on the pressure. So in case of gases, we'll always specify the pressure. So in case of liquids, all liquids at any condition, and in case of gas at 1 atmosphere, that representative elementary volume is 10 to the power minus 9 millimeter cube. That means in case of liquids and gas, we have to choose that small volume, 10 to the power minus 9 millimeter cube, and that will be the representative elementary volume, means that will be the volume in which there will be millions of molecules on one side, on the smaller side, and on the larger side the number of molecule distribution inside this small volume will be same, so that density inside this will be uniform, not varying even in this region. So this is the optimal volume that have been found, 10 to the power minus 9 millimeter cube. So now we can define density at a point, and we know it is not at exactly geometrical point, it's a small volume around it, and that volume is 10 to the power minus 9 millimeter cube. For example, how many molecules in this volume are there? For example, if we take air at 1 atmosphere pressure, at the standard atmosphere pressure, the number of molecules is 30 million. So we can see even this small volume chosen at 1 atmosphere, the number of molecules, air molecules present are 30 million. So this is enough molecule. If thousands of molecules per second come in and go out, their mass will not affect the overall mass of the rest of the millions of molecules. So this is perfect representative elementary volume. Now next we define the density at a point. Now, not the average density. We need that in some problems we know that that's very simple, but we want to see how the density is defined at a point and how the density varies from point to point. Now at a point we define it by choosing a smaller volume around that point, and that density will be exact density at a point, and that is that volume's mass whole mass is m, that volume mass is small, so delta m, divided by whole volume is v, and that volume is small, so delta v. And we know the limit, how small this delta v is. The limit of delta v approaches delta v elementary, this. So this becomes the definition for density at a point in a fluid. So when we say density at a point is some value, we mean all of this that I have said. We mean the volume around that contains some molecules, and the mass of those number of molecules divided by the volume of this small element is what we mean by the density at that point. And this way, when we move from this point to another next point, we'll still have 10 to the power minus 9 millimeter cube volume around that. So we're continuously moving from this to this. If we change point, take point here, so we mean this volume around that point. So this way we continuously move from one point to another point. So what happens is we are making fluid as a model, defining it in a way that property changes continuously from one point to another point. This is important. So properties, this way properties, any property change continuously from one point to another point. One point another point. And we know when properties change from one point to another point continuously, we call it smooth variation. Smooth variation. So properties vary smoothly. Now we know we have defined properties which vary smoothly inside a fluid. Now we want to analyze those properties, study those properties. How can we study that? Now, for example, we go to mathematics. We ask, we want to study these properties which vary smoothly in the fluid. How can we study them? And Mr. Mathematics tells us, we have a mathematical science that deals with science of smooth changes. We know the science of smooth change by definition is calculus. Calculus, mathematics branch, by definition is the science of smooth change. So we have properties that vary from one point to another point smoothly, continuously. So we can use mathematical branch calculus to define these, see how these properties vary inside the fluid continuously, smoothly. This is why, because we should be able to use calculus, we have defined these properties in such a way that so that they vary smoothly inside the fluid in order to make the use of the calculus. Okay, now we know we can define the overall density, average density of the fluid, and we can define density at a point in a different way that I explained, and that way we can say the properties vary continuously from one point to another point, smoothly from one point to another point, and we can use calculus to see how these properties vary mathematically. Now the next point is, now the definition, continuum fluid. Now this fluid in which properties vary continuously from one point to another point is called continuum fluid. This is the definition. So in continuum fluid, properties vary continuously from one point to another point, and they vary smoothly. We can use calculus to study the variation in those properties. This is the continuum fluid mechanics, which means we can apply the physical laws. We can apply the law of conservation of mass and find the continuity equation, because continuity equation in differential form, because we can use calculus on continuum fluid. We apply the law of conservation of momentum and we get the Navier-Stokes equation, and that Navier-Stokes equation is a differential equation because we could apply calculus on this continuum fluid, and we got that differential form of the law of conservation of momentum. Now we can apply the law of conservation of energy on this continuum fluid and get the differential form of the energy equation. This is how we get all those basic laws of physics in the differential equation form, because we defined the continuum fluid this way. Now there are other applications. All the applications that we see around us in the case of fluids use a continuum fluid. We see around us every property, every application uses mainly the continuum fluid, but there are many applications where we cannot use this continuum fluid concept. We cannot use a continuum model because we cannot define density even this way. And even this way we cannot justify that the density at a point can be defined and from one point to another the density varies continuously. One such example is, for example, atmosphere. As we move from the surface of the earth upwards, the density is large. We can definitely use it as a continuum model. But as we go very high at very high altitudes, at the altitude where satellites are there, where missiles reach, where these aircrafts are there, spacecrafts are there. So what we have there is the molecules the intermolecular distance between the air molecules becomes very large. What happens is, even if we take this volume 10 to the power 9 minus 9 millimeter cube volume, there will still be few molecules inside at that higher altitude, few molecules inside at that higher altitude. For example, at the ground level, at few kilometers, the molecules were around 30 million, but when we go high enough at the satellite levels, at those spacecraft levels, even this molecule, this elementary volume 10 to the power minus 9 millimeter cube would have much less number of molecules, and will still be having problem. Thousands of molecules coming out will significantly affect the density, and going in will significantly affect the density. In those situations we cannot use this continuum fluid. That fluid is called non-continuum fluid. Non-continuum fluid. And in continuum fluid we use the laws of conservation of law of conservation of mass, law of conservation of momentum, law of conservation of energy. All those principles we apply and we get differential form of the equation. Is because why differential? Because properties vary smoothly in continuum fluid. But in non-continuum fluid we apply same laws. We have same laws everywhere. We apply law of conservation of mass, law of conservation of energy, law of conservation of momentum. We apply all those laws, but the equations that we get are totally different from these equations because properties are not smoothly varying. So the equations will not be like the differential type of equations that we see in continuity equation or in the Navier-Stokes equation or the energy equation. They will be totally different. The equations are applied in a different way. The laws are applied in a different way, and we get different set of equations that are applicable only for the non-continuum fluid and not for continuum fluid. And the continuum fluid equations are applicable for continuum fluid. Non-continuum equations will be applied for non-continuum fluid. Now, so two cases becomes there. Two cases. One is this case, continuum fluid case, and another is non-continuum fluid case. So we use a parameter called mean free path to differentiate between the two. Mean free path. What is this? Mean free path. Suppose this is a molecule. This moves randomly and it collides with this molecule. Then it moves after collision. It takes this path, goes here and collides with this. What is the distance that this one molecule travels between two collisions? That is the free path of this molecule. Suppose we are talking about this particular molecule P1, and that distance, suppose this is that much distance it travels before colliding with another molecule. This is the free path of this particular molecule. We take another molecule, it will have its own free path. Because every molecule will not have same free path, they will have different, because some will travel more distance before another collision, some will travel less distance before another collision. So these are the individual free paths of the molecules. When we take average of all those free paths, it becomes the mean or average free path or mean free path, denoted by lambda, sometimes lambda m, mean free path of the molecules of a gas. So keep in mind this mean free path. This is like the average intermolecular distance between the molecules. The mean free path measures the average intermolecular spacing between the molecules. We can keep it in mind that way. Now we have two types of fluid applications or fluid problems that we want to study. For example, flow in a pipe. For example, flow in a pipe. Here, the dimension of the fluid, physical dimension of the fluid is this. This is the physical dimension of the fluid, and there are large number of molecules, and the free path is very small as compared to the physical dimension. So, free path is very small as compared to the physical dimension of the fluid problem, that fluid field, very small. So, if this fluid dimension, we call it characteristic length. Characteristic length is the length of the fluid flow, which measures how large the flow field is. So characteristic length, LC, characteristic length, and the mean free path is lambda m. Now two cases, continuum fluid and non-continuum fluid. For continuum fluid, this characteristic length will be much larger than the mean free path. So whenever we have a fluid flow problem in front of us and we see what is the characteristic length, we see what is the mean free path. If the characteristic length is much larger than the mean free path, we conclude it is a continuum fluid. And the equations that we have derived for continuum fluid, we will apply those equations here and study it. Now, in many cases, we will see the characteristic length is comparable to the mean free path. In that case, we cannot use the continuum, we cannot use it as a continuum fluid, and we cannot apply the continuum equations. We have to treat it as non-continuum fluid and use the non-continuum equations. Use a non-continuum theory. The theory that we study, that we have developed for continuum fluid, is called a continuum theory or continuum model, and the theory that we study for non-continuum fluid is called, we have different theories depending upon how small the characteristic length is compared to the mean free path. We have rarefied gas theory. If the characteristic length is even very comparable to this is rarefied gas theory is when characteristic length is larger than the mean free path, but is comparable. It's not that large that we can use continuum field, continuum model or continuum theory. And another is it is exactly comparable to this. So what we do is we use molecular theory directly, in which we study individual molecules using Lagrangian concept, using Lagrangian frame of reference for studying mechanics in the molecular theory. Means we study molecules individually in that case. So there are different theories if it turned out to be non-continuum fluid, but the studying the non-continuum fluid is out of the scope of the bachelor course of the BTech course or B course in fluid mechanics, and even in PG courses we mostly deal with the continuum field. So this non-continuum fluid is even under research yet. It's under research, and it is we started studying in PhD or late PG courses. So our main focus is on continuum fluid, in which we see the differential form of equations. So this was about continuum and non-continuum fluids, and we saw that we can study fluid in two ways. One way where fluid can be treated as continuum fluid, in which property can be defined at a point. Because of that 10 to the power minus 9 millimeter cube volume, we can define it at a point, and the properties vary smoothly and continuously from one point to another point, so that we can apply calculus. The differential equation differential equations are obtained when applying the basic principle of physics, basic laws of physics. And another side, we have non-continuum fluid, in which the intermolecular spacing is very large as compared to the characteristic length. As compared to the characteristic length, it becomes comparable, so that we cannot define property at a point and cannot say the properties vary smoothly from one point to another point. And in that case, which is obviously out of the scope of this subject for BTech course, we define it as non-continuum fluid, and we have to use different theories which are called like rarefied gas theory or the molecular theory. So mainly we deal with the situations where characteristic length, the flow dimension, flow field dimension is extremely large or very, very large as compared to the mean free path. Another example where we use non-continuum one was where the intermolecular spacing gets larger. For example, when we go at higher altitudes, the intermolecular spacing increases. We have to use non-continuum theory. Another example is when system itself is very small. For example, MEMS, micro electromechanical systems are becoming popular. They are very microscopic size systems. So since they are microscopic scale systems, so if the fluid flows in them, the fluid characteristic length will be very small. It will be very small compared to this mean free path. In those situations, the non-continuum or rarefied gas theory is used. That's why it is becoming more and more popular because of this invention of these micro electromechanical systems. So this was all about continuum and non-continuum fluids and the two theories that we use, the continuum theory for continuum mechanics and rarefied gas theory and molecular theory for non-continuum mechanics. Now we know that we have a fluid in front of us. Whether we have to use Lagrangian or Eulerian concept, we know it is fluid. We are interested in bulk, so we have to use Eulerian framework. We know whether it's a system or control volume. It's a Eulerian concept. Fluid flowing in, flowing out. It's a control volume concept. We will use control volume concept, Eulerian approach. And then we know whether this fluid can be studied with continuum or non-continuum. If the characteristic length, fluid dimension is much larger than the mean free path, continuum. If it is comparable, non-continuum. Now we are ready to start studying a fluid flow problem. Any fluid flow problem that comes in the category of continuum fluid. But before that, we have just defined one property, which is density. There are many properties that we need to study in order to later start studying how these properties change when fluid flow, when different kinds of fluid, there are different kinds of fluids, how these properties change. And even before that, we take the simplest case when fluid itself is not even in motion, the velocity of the fluid is zero, the fluid is stationary. What properties are relevant for us in that situation and how they vary, and what are various forces that we need to study, and that will be for in upcoming videos. That will be all for today's video. Thank you.